In this video, we are looking at the line of best fit. I think this is one of the most underappreciated and undervalued elements of mathematics that students study in secondary school. As a maths teacher, I've been guilty of skimming over it. The line of best fit is actually a topic studied lots in university degrees such as statistics or economics, where people are trying to identify the relationship between one variable and another variable. And having an understanding of the relationships between different variables gives us more ways in which we can shape the world around us. And that's why I think this is a hugely important topic. So let's start with some data. I've collected two pieces of information about students in my class and recorded it in a table. For each student, I've recorded the number of hours they studied and the percentage that they got in a recent maths exam. So, for example, the first person that I asked studied for 21 hours and they got 93% in the exam. The last person I asked studied for 18 hours and they got 80%. So, just looking at this data, can we see any relationship? Well, I can compare the first two people. The person that studied 21 hours got 93%, and that was a lot higher than the person that studied for 0 hours. They did no studying at all. They only got 60%. So that suggests that a student who studies more may do better in an exam. However, I could also compare the student that studied 0 hours and got 60% to the student that studied 1 hour and only got 38%. If we just looked at those 2 points, then maybe we'd reach the conclusion that studying more makes you do worse on an exam. Well, there are lots of different factors at play here. The best way to start visualizing a relationship is to plot all the points on a scatter diagram. So let's do that. It's worth noting here that the students in the table aren't in any kind of order at the minute, but putting the information that we have into a scatter diagram will help us see an order and a pattern. Along the x-axis, I have the hours studied, and that's going up in fives. And on the y-axis, I have the performance on the exam. These are our two variables: hours studied and performance on the exam. I'm going to plot those points on the diagram and cross them off as I go. So the first person studied for 21 hours and got 93%, so I'm going to put that cross there and cross it off. The next person studied for 0 hours and got 60%. As you can see, I'm plotting the different points on the scatter graph and crossing the observation off the table as I go. So now that I've plotted my points on the scatter graph, I can turn back to looking for that relationship. Just from what I see on the scatter graph, it looks like there's a positive relationship between hours studied and performance on the exam. We could call that a positive correlation. That's the specific word we use in this context. However, a better way to visualize this relationship would be with a line of best fit. So how do we draw a line of best fit? Well, I'm going to start by drawing a bad line of best fit, and that will help us identify the good features of a line of best fit. When asked to draw a line of best fit, I've seen students draw lines like this before. This isn't a line of best fit because it doesn't fit the data. When I asked students to explain why they drew that line, they said they had been told to draw a line of best fit such that the same number of points were on each side of the line. There are 16 points on total, and with this line, there are 8 points to the bottom left of it, and there are 8 points above and to the right of it. So if that was all that mattered, then this would be a good line. However, we can see it doesn't fit the data. It's not even a line of good fit, let alone being the line of best fit. But I can go a bit further than just saying it doesn't fit the data. Let's try and quantify and visualize how much it doesn't fit the data. So for each point, I'm going to draw a line showing how far out that trend line is from each point. In university, they use the word residual to describe the distance between the line and each point. There was my first bar from the point at 60 up to the trend line, and there's the second one, and so on and so on. You can see for each point that I took from the table, I'm drawing a bar from the point to the trend line. So let's find the total height of all of those bars, the sum of the residuals. Let's put that sum of residuals on the right-hand side. Actually, because they're not all going to fit on the screen, I'm going to make each of them a quarter of their original size. But this will still make sense. Now, the line of best fit would be the line that makes that yellow bar on the right-hand side the smallest possible line. It would be the line that minimises the sum of the residuals. So, what will that line look like? If I rotate my trend line to here, we can see that the residuals, remember that's how far out it is for each point, are much smaller. And the sum of the residuals, the total size of this yellow bar on the right-hand side, is almost a quarter of what we started with. So by going from this trend line to the line of best fit, we have improved our line of best fit by 4 times, because the sum of the residuals, this yellow bar, is a quarter of what it originally was. Now you might be looking at this and thinking to yourself, well, surely the line of best fit would have no yellow bar at all. It would completely fit the data. And I see where you're coming from if you think that. But for that to be true, it would mean our line would go exactly through each point. And that's a problem that we call overfitting. The danger of overfitting becomes more obvious when we try and predict how another student might have performed on this exam. So if we take a student that was off sick on the day of the test, but they told me that they studied 3.5 hours for the exam, I could try and use the information from the rest of the class to predict how well they would have done on the exam. So using the line of best fit here, 3.5 hours corresponds to just under 60%, around 59%. But if we used our overfitted line, which goes exactly through each point, then I would end up predicting them a mark of just over 70. And that's unfair on the rest of the class because that mark is overly determined by the 2 points next to it, rather than the class as a whole. So at the start of this video, I mentioned studying statistics or economics at university and looking at lines of best fit. And throughout the video, I've talked about the sum of residuals. And at university, this would be called a regression. In this video, I've done this entirely visually. There's been no calculations involved at all. But at university, you'd look at this from a much more mathematical perspective, trying to find the exact equation of that line of best fit. And that's something I really enjoyed studying at university because it's the foundation of research that shapes government policy. I hope you found this video useful and a good representation of a topic that I think is often overlooked at school. As always, if you have any other topics you'd like me to cover, don't be afraid to leave a comment as I'm always on the lookout for new ideas. Thanks, guys.